Okay, so it's time again, and thanks again for joining us. Today, we are very pleased to have Przemyslaw Wojtaszczyk from Polish Academy, and he's speaking on quasi-greedy bases and p-Banach spaces. Please go ahead.
Okay, thank you for having me on this, I think, worldwide meeting or seminar. And as you can see, this is, we'll talk about joint work with Fernando Albeck and Jose Luis Ansorena. And basically, as usually titles go, I mean, they are more general than reality. Now, the talk is based on our joint paper, which is available online by mathematician Annalen. And in reality, it deals only with the LP space, little LP space, and certain quotient kernels of the certain quotient maps from LP onto capital LP. To the old people like me, I mean, you can recall that this kernel in the case p equal 1 was introduced by Joram Lindenstrauss as an example of kind of a strange space. And we kind of continued the strangeness of this space. So, okay, formally speaking, this symbol here, I think it is K, and this will be denote this kernel. And we studied a conditional quasi-greedy basis in those two spaces, basically. So let me start with the definitions, which will go throughout the whole talk. So, I mean, the Schauder basis, everybody knows what it is. But we kind of usually assume that it is normalized or almost normalized in the sense that it will have not norm 1 all the time, but something like 2 to 1 over p or something like this. The definition in the p-Banach space is exactly the same as for the Banach space. And just to recall, I hope everybody knows what the p-Banach space is, but if somebody doesn't, let's jump in and, I mean, breaks in and ask the question. Now, the coordinate functional of the basis, if it is Schauder basis, then the coordinate functional of the basis are continuous, they are bounded exactly like in the Banach space, and the kind of a finite operators projections onto this piece of the basis are continuous. And now the whole business of greedy basis and quasi-greedy basis and almost greedy basis and all the other greedy type bases is this operator. Now, this GM is called greedy approximation, and it's written as SA of X, but the set X, A, which is here, is chosen by the, is adapted to the element X. So this is not fixed. And it is simply the element where the vector, this is simply a set where the vector X has M biggest coefficients up to the absolute value. Forget about the equalities, that doesn't matter. Always we can assume that it strongly decreases and doesn't change. Now, the basis is quasi-greedy if those operators are uniformly bounded. In other words, there are, for each M, there's an operator, and we want that be for each A, X, and each M, or rather for this operator for each M, and for each X, this was uniformly bounded at this estimate. This is equivalent, however, it is not very trivial, that the limit of GM of X is X for every X in X. Now, this was studied before the greedy basis because in various settings, because basically this convergence boils down to the convergence of this series here or here, but when we arrange the coefficient in a decreasing way. So we simply have this standard coefficient of the basis, and then coefficient can be big, small, whatever, jump back and up forth. But we say that we want to have the decreasing, and then we look the convergence or not. Okay, and this next definition that the basis is democratic, and this definition means that whenever we take the sum of elements from the basis, finite sum, but arbitrary, the norm of the sum is effectively depends only on the number of elements. So this is why the Volodya Tymlakov, who I think with Stephen Koniagin, they officially put this name, and this is kind of a political joke, let's say. Okay. Now, obviously, the unconditional basis is greedy because we rearrange for the unconditional basis, you admit all the rearrangement, and here we look at only at one. So there was already immediately a question of conditional quasi-greedy basis. I mean, the ad hoc example was invented by Volodya Tymlakov and Sergei Koniagin, but then I invented, so they had an ad hoc exam. I produced the example, which is this theorem here, or this statement for p equal 2. I was mainly interested in the quasi-greedy, conditional quasi-greedy basis in L2. And then Steve Dilworth, Nigel Carlton, and Denka Kutsarova produced the different technology will allows, I mean, there's no general theorem, but I mean, I formulate it like this for any p except infinity. For C0, this doesn't work. And then there was some research what can happen with quasi-greedy basis, and also they proved that the L infinity script L infinity spaces practically do not have quasi-greedy basis. There is only one exception, namely C0, and the only quasi-greedy basis which can happen in C0 is a unit vector basis. So I mean, it's not very. The result is very nice, but I mean, as a set of examples, it's not very great. Now, it is relatively easy to see, and it was observed like 20 years ago, that if the basis is quasi-greedy, then if we take a sum of vector bases without coefficients, we can put pluses or minuses, and this will not change the norm very much. So they say that the condition, that the quasi-greedy basis is unconditional for constant coefficient, let's say. Oh, sorry. And then we see, once you are in business of looking for unconditional basis or quasi-greedy unconditional basis, it is natural to ask the question, I mean, to measure this, how conditional it is, and the natural is this number conditionally constant of the basis. For each m, we look for all these partial projections onto m element set or smaller, and we take the supremum of the norm, and this is, if this stays bounded independently of the set and m, then we have unconditional basis. If not, the basis is conditional, and these numbers, how they grow, I mean, they give us how badly conditional it is. And basically, the observation for quasi-greedy basis is that those constants do not grow too much. Namely, they behave like logarithm or better in another small place. Okay, so this is now the construction. As I said, I will be doing the looking at the quotient. So maybe this is a way to build the quotient. It is a way of building the quotient, but let's start with the construction of the certain tree of subintervals of the interval 0, 1. So we start with the sequence of integers, which those integers are assumed to be greater or equal than 1, otherwise they're arbitrary. And we create the intervals. The first interval is the whole interval, 0, 1. Then we divide this first interval into D1 equal intervals. So in here I do this drawing is for this sequence here. So we divide it into 3. Excuse me?
Oye, ¿este de los mostachos?
No, I don't understand.
That was probably.
No?
Go ahead. Yeah.
Okay, so this sequence governs how we divide those intervals. It says the first interval is divided into 3 equals. Then the second interval is divided by this number intervals. The third interval is divided by whatever it is here. And the fourth interval is divided by the fourth number here. And then we calculate, and then this is 5th, this is 6th, this is 7th, and divide it further. So we have such a tree of smaller and smaller intervals, but they can be kind of divided differently, depending on this sequence. And then we define the operator, which goes from little LP into capital LP by sending the kth unit vector into the characteristic function of the kth interval, normalized to have it norm 1. So this is basically, here goes the first unit vector basis, this is the second, the third, the fourth, fifth, sixth, etc. So this is an interval, the operator, which goes from LP little to capital LP. And basically we'll be interested in the kernel of this operator. Now we define xk, and this will stay with us for the time of the talk, as the sum of as unit vector and sum of all the vectors which the intervals whose intervals are below xk. So for example, here is this 8. It will get 8 unit vector, and the sum of those 3 vectors, which will be turned out here, and I'm too lazy to calculate all this. But formally, I mean, in numbers or in formulas, it is written here. We define sigma k is this sum, and this sum gives us this vector. Now, if you look at it, you will realize that this number, hopefully you will realize that those numbers are chosen in such a way that if this ek goes to one interval, all those intervals below cover this interval here, and this sum, if this was a number, this sum will give the same number, only with the minus. So the vector, the operator qp, will kill this vector. So those vectors are in the kernel. And that's more or less how you can see how those vectors add up and how the vectors look like. I mean, the black one is here, the next one is green. It has one vector here, and then some bunch of green here, and then they go up. So in a sense, the way to think is that this vector x, say 15, has at 15th place a unit vector, and then somewhere far away will have a number of vectors, but of a smaller unit vector, but of the or coordinate, but of the smaller value. Okay, so this was more or less. And the following is pretty clear after all, namely that this operator has norm 1, it is obvious, it is a quotient map, and this is also pretty clear that this is 0, I basically explained, and then the space, which will be called this k, Gothic k, p of delta, which is a kernel. First it is a kernel, and then the kernel is the span of all those vectors. This requires some arguments, but now we are not so bright to invent everything from scratch. So this was, as I said, this for p equal 1 and for delta equal 2 to 2. That means that the other case, this was invented and analyzed by Joram Lindenstrauss in his old paper. And then in quasi-greedy basis, it was used by Steve Dilworth and David Mitra, and they used this to construct a conditional quasi-greedy basis in L1. So if they take this kernel, it use this access and get the basis in L1. Okay. Now, basically, this is an easy lemma that if we have delta, whatever delta we take, this space Kp of delta contains a subspace isometric to LP, little LP, and complemented in the whole LP. Remember, this is a subspace of LP, but this subspace of this chaos LP is complemented in the whole LP. And basically, this is here is a proof with the projection. Okay, now here is a comment. You see, there exists a subspace of Z in little LP if P is less than 1, which is isometric to LP, and no complemented subspace of the subspace is complemented in LP. Simply the now this is important from our point of view, because somewhere later you see this property was very essential when you do for LP. In the old paper by Linden and Strauss and Rosenthal, where they proved that all the kernels of the map from L1 onto capital L1 are the same. They are isomorphic and actually located in the same way. Now, for P less than 1, honestly, I don't know what is a real situation. However, Nigel Carlton, when he was studying this, observed that the proof which was given, I think he quoted the book by Linda Safriri, but that this property is essential. So in other words, what they prove is that if the subspace LP has this property and the other subspace has the same property that it contains this, then they are located, then they are the same. But this we don't know for all subspaces. So anyway, okay. And then by this KPN, we will denote the finite span of this sequence xk. And now we have simply the proposition for P between 1 and infinity. Whenever possible, we include P equal 1 because it doesn't hurt us. Any sequence, the n, this is a bimonotone Schauder basis in this space Kp. And for every n, the Banach-Mazur distance from Kpn to little lpn is not larger than 2 to 1 over P. And this is, okay, so what? Look for calculation above. Okay, look here. Let's think about monotonicity. What happens? We kill out the fourth coefficient. This is why I put alpha here. We kick out the fourth coefficient. What happens? This piece here disappears. So we lose norm from norm, we lose alpha. And now what happens here? Well, at the worst case, we can increase the norm by removing alpha because, I mean, this was, but not more than alpha. So we lose more norm in this sense and in here. And that means that this projection has norm 1. We go the other direction, this is the same. Okay. Now, to get this Banach-Mazur distance, we simply, I mean, this xn is a basis, it's no good, clearly, this has to be different from unit vector basis, but we construct the basis which gives this isomorphism, and this is described here. So basically, we build the unit vectors, which sits, I mean, unit vectors up to the place n. And then it has some coefficient far away, but it's sufficient too. Okay, now let's go back to script LP spaces. Because there's a ready result by Nigel Carlton. Nigel Carlton introduced this definition of script LP spaces. So, okay, the closed subspace of a quasi-Banach space is locally complemented if there is a constant locally complemented in X is complemented in Y, if for every subspace of Y, finite dimensional. They exist an operator into X, into the smaller subspace, which first is uniformly bounded, a norm, depending on that, and is pretty close to identity on the part of this finite dimensional subspace which sits in this space X. And then, so that is the general definition, and then the Banach, the quasi-Banach space, in particular the Banach space, is a script LP space, P between 0 and infinity this time, if it is isomorphic to a locally complemented subspace of some measure space LP of mu. Okay, that is a definition, and we use it. We use not this definition, but we use this. I mean, we get the result that our space, this kernel, is a script LP space, and then we get this isomorphism. This is also that somehow that all the spaces we construct, all the kernels we construct by this method, independent of delta, are isomorphic. Clearly, they are different if P are different. This is a locally complemented in LP, so it is script LP space. It is not complemented in LP, little LP, and it does not have an unconditional basis. So this we have for granted. For this space KP, not for granted, but it follows from this this Carlton study of script LP spaces. Do I have? Yeah. Let me say already right now what is the situation. You see, this definition, as I said, applies also for Banach spaces. And the difference for Banach between this and the Banach space, this definition for Banach spaces and as between the classical, say, definition by Lindenstrauss-Belczynski, is that if it is the same for P equal 1 and P equal infinity. For P between 1 and infinity, the difference is that we throw in away Hilbert space. The Hilbert space is script LP space with this definition, obviously script LP for any P between 1 to infinity. Otherwise, it's fine. However, for P less than 1, this is at least more manageable. And also, it's kind of nicer because, as far as I know, the people didn't decide if LP, little L, L1 half, say, LP on the unit interval is script LP space if we apply the Lindenstrauss-Belczynski definition, whenever it is clearly, or at least easily, LP space with this definition. So somehow it is nice to have LP spaces to be script LP spaces. Okay. And now democracy. Democracy, we basically I describe what it is, but to put it into some more precise numbers, we define lower democracy constant and upper democracy constant, which is phi L and lower, and M is a number, and this is infimum of the sums of the longer than M sums, and this is a supremum of the shorter than M sums of the basis vectors, etc. Now, that means clearly that the basis is democratic if those two things are comparable. Clearly, lower is less than upper. And now there is a proposition which says that if we have delta and we have the sequence of integer, and then this basis is democratic basis for this KP, and lower and upper estimate democracy function satisfy from below it is some number m to 1 over p, and from above is 2 times m to 1 over p. Now, once more, we can look at this same picture we had, except there's no alpha here. And basically, you realize, I mean, that it is trivial. I mean, look at this first place forward I once. Forget about the rest. Now look, this is in each place there is 1 and some number. the biggest of this number is 2 to minus 1 over p. The 3 to minus 1 over p is smaller. So each of those numbers from 1 up to 4 coefficient is at least 1 minus 1 over 2p. So the norm of the whole mass is number of those vectors times 1 over minus 2 over r of p. That's the proof of this estimate. And then this is simply by triangle inequality as far as it exists in p-Banach spaces. So this is pretty obvious. And now I have, well, now I say for p-Banach spaces, what goes over? I mean, unconditional basis is still quasi-greedy. This condition holds. The definition of unconditionality or conditionality constant exactly holds. The only difference is that this a priori upper estimate for conditionality constant is log m to 1 over p. P has to come in someplace in this. So, okay. And now we basically, I'm ready to start with some theorems. Namely, this sequence for p between 1, any delta, any integer, the basis x n is a quasi-greedy basis for this kp of delta, and quantitatively this norm of this gm is less than or equal than some numbers which depends on p. Now, the sketch of the proof, really this requires some calculation, maybe not very well. I'm bad in calculation, so for my mind, awful. But basically, what we have to say, we have vector x. We have to split into the a with the big coordinates, which will be g, and then the b, which has smaller coordinates. So it will look something like this. And now, the canonical basis, which shows elements which are here, or rather we have them here. We split the canonical unit vector basis in two sets, A and B, and this is this set, because this vector x has a unit vector basis kind of vector prominently in this definition. This has from A and this has from B. And then we have those sets where this vectors from here have those smaller coefficients, and this will be SA. Formally it is SA equals a union of supports of this Rj, which is, remember, xj equals unit vector with j plus this reminder, which is the smaller coefficient. And then the set B is the same. And then we look at the intersection of all those. We have what, four sets. Well, those two are disjoint. So actually those two are also disjoint, so those interactions are somehow a little less than you can expect. But then you look at all the most possible intersections and complement to the intersections, and you say, oh, here is a small vector with a small coefficient, so, and then there are the other one which is a big, and you do it. That's boring maybe, but still fun. Okay. Nowadays we had to introduce the additional condition which we didn't have earlier, namely that this sequence delta is non-decreasing. And then we can compute the conditionality constant of the basis xm. Now there are two. Well, forget about this GM. This some function. It's explained below, but let's skip it. Okay. The first thing which is worth your attention is that basically it says that the unconditionality constant of the whole basis, infinite, is the same as the conditionality constants of this first piece in the small space. So somehow all conditional stuff happens at the beginning of the thing. And then there is a expression which gives use some number gamma of m, and then the CP, which is somewhere in calculations I didn't want. Now, what is this gamma? Well, first we had the sigma. We add up the dj's. Now, since sigma is increasing, then and sigma of 1 equals 2, then we look at this sequence. Namely, we take iterates of sigma. We start with sigma of 1, which is 2, then we take sigma of 2, this will be sigma 2 because it's an iteration of second iteration, and then we take sigma of sigma 2 will be sigma 3 of 1, etc., etc. This will be lambda of n. And this is also increasing. So that means that it has an inverse. Well, not exactly, because it is constant most of the time actually, but it has left inverse, whatever, I mean, it is clear. And this left inverse goes from natural number to natural number. So that's, if you don't follow here, there will be an example which I will show that this is more or less computed. But anyway, there's a number here, which we can calculate from delta. And this gives this, this conditionality constant. Okay. So how we prove it? Well, surprisingly enough, or maybe not surprisingly enough, this requires the calculation of biorthogonal functionals, because we deal with the projections, something like this. Actually, we deal with operators which have some epsilons here, but epsilon is plus or minus 1. And for this, we would like to have formulas for the coefficient functionals. Now, if you look only on Kp, then the functional biorthogonal function is a functional which is 1 at x something, and then 0 on all other x's. However, we would like to calculate them as a sequence. In other words, as an element of L infinity, say, etc. Now, there are problems here. First problem is that there's a problem with p-Banach theorem, but if you write down something, you write down something. But it is absolutely clear that this extension is not unique. You know, there may be many such functionals. So what we do is that we, I will go later to those functionals, but those are certain, special L infinity elements which restricted to Kp are biorthogonal functional. And then we take arbitrary element like this, arbitrary operator like this, which is something which should come into here. Maybe I wrote only without pluses or minuses, but this will turn out to be almost the same. And then we push this set A to the left to get to the beginning. And then we show with each step, when we move one of these J's to the left, we show that the norm increases. So eventually, when we get to the very beginning, we'll get the estimate of the norm of this thing by the norm of the very similar thing, but with A being 1, 2, 3 up to whatever. And then we have those functionals explicit, and we estimate them by basically by the triangle inequality, and we get something like this. And to go backwards, I mean, to the other estimate, we only have to work with this KPM. That means with the first M vectors, x1, xk. And basically, we construct the vector for each M, we construct the vector ym in this, which is in here, so it's of this form. But basically, it is 1 at the first place and 0 on all the other places, obviously only as long as we can. That means up to the M. In other words, we write this vector, and then there's something left for in the bigger coefficients. And we look at this vector, and the way we construct it, we get a ym norm of ym equals 2. But if we change the coefficients, those coefficients which will turn out here will be some positive, negative, etc. If we put absolute value, we end up with the estimate. So this is simply the matter of pointing out the one vector which does the job. Okay, now, once we have this, and we have gamma, we know that this Kp is a one Banach space up to isomorphism. And we have a lot of bases. They're all quasi-greedy and democratic, but they come out of different deltas. So we would like to have deltas which give different gammas, because recall that we get this is basically gamma to 1 over p. So if you want to have vectors which have different conditionality bases, which have different conditionality constant, we would like to have delta sequences, delta for which gamma m are different. Well, okay, there's a nice proposition here which says that for any increasing concave function with phi equals 0, there exists a non-decreasing sequence delta of integers such that the associated function gamma satisfies that gamma m is phi of log m. In other words, we can get a lot of sequences where this will produce a different growth of this gamma. Now, actually, when we tried to do it, well, I will go to it later. Okay, so now what do we have? The theorem, which is basically one of those that we wanted, is that if V be either LP or KP for P between 1 and infinity, then for every concave function phi with phi equals 0, there exists an almost greedy Schauder basis, which has this growth of conditionality constant. Now, almost greedy simply means quasi-greedy and democratic. So this we actually, for the case LP, we already proved. And for LP, we basically proceed the standard way. We include this basis by pieces. We take this finite dimensional space, which depends on D and N. And we know that this piece has the x's in this piece. They are quasi-greedy, they are democratic with this constant, and they have some kind of a constant increasing conditionally constant. And moreover, they are distant from LPN by 2 to 1 over p. So we take the infinite direct sum in the sense p. And then, okay, now conditionality constant is absolutely clear that it goes to the same, is the same as for the whole Kp, and then the rest is also pretty clear. We just for the fun of it, we have to check that quasi-greedy is preserved by this type, and democratic is preserved because all those spaces have the same democratic constant. So that's here. And the desired basis is obviously the basis xj in each piece separately. Now, you see, almost greedy is a funny and interesting concept, I think, because basically this almost greedy, which here is quasi-greedy and democratic, okay, quasi-greedy I already talked about for whatever, more than half hour, so you may have got used to it, but this almost greedy is fine. But look, almost greedy is equivalent to this estimate. Now, in other words, it says that this picking the biggest coefficients is the best that you can do as long as you pick the other, among all the other coefficients. Almost the best, because if you choose the similar sums, but taking other coefficients, which is somehow interesting, I think. Anyway. Now we are going back to this to the Biorthogonal functional, because they are also interested once you have the basis. Interesting. Once we have the basis, we would like to have this. Now, for Banach, if we have p less than 1, then we take the Banach envelope on this Kp, and this turns out to be L1. And this basis is a basis, Biorthogonal functions are also then turn out to be a basis in the dual of this Kp. And this basis is equivalent to the unit vector basis in C0, because this dual is C0. So this is not big fun. However, for p equals 1, and this was already applied earlier, investigated earlier, but without this delta being dyadic, we obtain a basis. Those sequences which we produced here turn out to be a basis in C0, which sits in L infinity. And they simply have conditionality constant as equal to gamma, and they are not quasi-greedy, and this quasi-greedy coefficient is also kind of grows like gamma to the m. So those are kind of modulo those numbers. This was known to, I think, Holub and Rutherford were investigating this as a basis in C0. And now I'm already almost closing the study. So you see, I mentioned those papers by, this by an old paper by Lindenstrauss, whatever. So the paper of Lindenstrauss on which this quotient was put into public is this old papers in Bulletin of Polish Academy of Sciences. Then Dilworth and Mitra is a paper in Studia. Lindenstrauss and Rosenthal is a paper on automorphism from LC0, L1, and it is in Israel journal here. Now, Carlton study of script LP spaces for P is also, all those papers I mentioned kind of in the on the go is, and this Holub and Rutherford also a while ago they investigated the not only this basis in C0, but some others which they call cures. Now, if you are interested to know everything, or you want to know, or maybe too much more that you want to know about various greedy type bases in quasi-Banach spaces, you can find in the paper which we prepared with, Fernando Albia, Jose Luis Anzorena, and Pablo Berna and myself, and the paper is to show up in Dissertaciones Matematice. If you ever saw Dissertaciones, you can see that it has to be pretty long. Let me, before I thank you for your attention, let me take one thing. I was using here Schauder basis, and however, you see, the Schauder basis is sometimes useful in this context, but really speaking, if you take a Schauder basis and you permutate any other number, any other way, it stops being a Schauder basis, but it does not stop to be a quasi-greedy or greedy, because it depends on this G. And G is a set where the coefficients are bigger. This has no relation to the order of the basis. So in this sense, it is very natural to study quasi-greedy or greedy basis in context of, how it is called, Biorthogonal system. I'm getting old. This is okay. So anyway, this is much more. This a priori it can be much more general, but somehow in some places it's useful to have Schauder basis. So you see this all mixed up with some papers are for Schauder basis, some papers are for Markuszewicz or Markuszewicz basis, and also some papers claim that the things are obvious for p less than 1. Some claim that L better not. So one of the aims of this paper was to bring some kind of order in this. So we tried to as much. Okay, anyway, thank you for your attention.
Thank you so much for the talk. So we can open for questions and comments. What is this picture from?
Oh, it is a monument which I like very much of the Polish poet. As you can see, for the monument, it's really strange.
Nice. Any math questions?
Oui?
I'm asking people any math questions or comments. Okay, I guess, yeah, go ahead. Someone.
Well, I mean, just a small query.
Excuse me?
Yeah, Professor Wojtaszczyk, this is Sophie here.
Yes. What was the question?
In case of P LP spaces for P strictly less than 1, being locally locally complemented is the same thing as being a Lipschitz retract?
Locally, I don't know.
I have a question. It's complain the CDC data stage. It's complaining of field, and I cannot find this field because I have different names. I don't know where it's coming from.
Sorry?
It's the same job, and name of the job is GB and payroll, new and payroll CDC XFM final in general client folder.
I have no idea.
No, not compiling when I running.
Please put in chat. I don't understand what you're saying. Okay, so any other math questions?
I didn't get Professor Wojtaszczyk's answer.
He said he doesn't know.
Okay, okay.
Yeah. All right. Thanks again for the nice talk. I'll stop recording, but we can continue conversations after.